Hello, welcome to a new edition of HPL Discovery. In this edition, we are going to delve into the workings of a binary world. You've probably heard that in computers, everything is stored as zeros and ones, binary. So, our communication is a lot more than just zeros and ones, right? We have words, we have numbers, we have sounds, we have pictures. So how does the computer store all of this information as just zeros and ones? So let's explore how the computer stores and communicates in zeros and ones for numbers and text and pictures. In your Discovery Kit, you have instructions for two activities. One to look into numbers and letters, and the other to look into pictures. You will also find a card that has different numbers of dots, and you will find a 2B pencil, a graph sheet, and at home you will need a pair of scissors, a rough piece of paper, and a pencil. Let's begin with the first activity, which is looking at the binary world in terms of numbers and text. Cut out all the squares of the dots and place them on the table with the highest number of dots to your left and the lowest number of dots to the right. Now, when all the dots are showing like this, then we have represented a 1, 1, 1, 1, 1, and 1. So how do we represent 0? We represent 0 by not showing the dots. So this would be, these dots are showing, so that is 1 and 1. So this will be a 0, and this, because again the dots are not showing, will be a 0. So any card that does not show the dots is a 0, and a card that is showing its dots is a 1. Okay, so now let's make these two 0. And let's see, what number does this arrangement represent? It represents the number of dots that you can count here. So it's 1, 2, and 3. So this arrangement of 0, 0, 0, 0, 1, and 1 represents the number 3. As you can see, we have represented the number 3 as just zeros and ones. So 0, 0, 0, 0, 1, 1. So by flipping different cards, you can represent different numbers as zeros and ones. For example, if we flip these two cards, then it would represent the number 1, 2, 3, 4, 5. That's right. So 0, 0, 0, 1, 0, 1 is equivalent to 5 in decimal. Now it's your turn. Try and represent different numbers by flipping different cards. Now each of these cards is a binary digit, or a bit for short. And because we are using the 6 bits together to represent just one number, the 6 bits together is called a byte. So now let's look at how letters are represented. Use a simple formula that says A is equal to 1, B is equal to 2, C is equal to 3, and so on. So, which letter would this represent? So A is 1, B is 2, C is 3, D is 4, E is 5. So 000101 would represent the letter E. So this way, with just zeros and 1, we can represent numbers and digits. That was not too hard, right? Zeros and ones could represent huge numbers by just using 6 different bits. How about pictures? Pictures are a lot more complex. So let's look at a different way to represent pictures in numbers. Now we are looking at the second activity in your kit. There is a set of numbers in the instruction sheet. So for these numbers, the first digit represents the number of white squares on your graph sheet. And the second digit represents the number of black squares in your graph sheet. So the first set of numbers here is 2 and 7. So let's see. We've got 2 white squares and then 7 black squares. So take your 2B pencil and color in the 7 black squares. 3, 6, 7, and 7. And each set of numbers represents one line in your graph sheet. So when you go to the next 2 or more numbers, go to the next line in your graph sheet. So the second one also says 2 and 7, so we're going to just go ahead and make the 2 and 7 2 blank and 7 black squares. So in this way, color in all the different lines of code that is here. And then hold your picture far away. Once you have decoded all the lines of this picture, you should be able to see your picture. Hold it far away so it looks more smoother. You've probably heard that your camera or your computer screen has a resolution of so many megapixels. So megapixel is 1 million pixels. If the square on your graph sheet represents 1 pixel, then your screen has more than 1 million such squares. So putting information about the millions of squares or pixels that are on a screen, or to store information about one picture being millions of pixels, then you have to have a lot of storage. To solve this problem, pixels or pictures are stored in code. This particular activity showed you one way of storing pictures in code. This way is called the run length code, where the length of a single color is specified in numbers. As you can see, this works best when the colors are few and the picture is pretty simple. So it's mostly used in fax machines. So now it's your turn to delve into the world of binary workings and try and draw your own picture and code it using the run length code. And see if a family member or a friend can decode it into a picture. Don't show them the picture. Hope you enjoyed delving into the world and workings of a binary world. Until next time. Bye.